So in the next question we're told they plot the free body diagram of the backhoe and its members, assuming that the members have no mass and are being connected under the bucket, and its coordinates have a weight W and the center of gravity G. And then based on this model, give a realistic magnitude of mass M. So for me, I went ahead and gave a weight that is more than a ton, that is 1500 kilogram, hoping that it's a realistic weight. So I converted this to weight by multiplied by G. I got 14.7 kilonewton. All right. Then you are told determine the force generated in the hydraulic cylinders EF and AD. If you look closely, you'll realize that most of those connections that are making up this backhoe are pin connection. So it means that those members are rotating about those points. Right, so it's a pin support, pin connection, something of that sort. So to draw the free body diagram, I represented the whole shape of it and how the load is being carried, how it's being lifted. So the backhoe is lifting this weight, and for it to be able to lift this weight, it has to exert some force on these arms, or you can say hydraulic cylinders, so that you can be able to either hold this weight in a stable manner so that it cannot fall or topple. So, and also these cylinders themselves, if you look at how the connections are, when a force, when this cylinder tries to elongate, when it elongates, it tries to push this joint forward, because this is a pin connection. When this one is pushed forward, this arm tends to fold this way, so it pushes forward, this one comes this way. Okay, and when it retreats, we also see this arm shortening, so it is pulling this point this way, because this is a pin, so this one will rotate that way. Okay, and at this point here we have this is another hydraulic cylinder here. So when this arm elongates, it has the capacity to lift the whole of this arm, to lift the whole, so it is pushes up. It can push up because this connection is carrying these two members, so it can push upward this way, and it lifts the whole of these other members. Yeah, this is how I represent my free body diagram. So we have the weight here and we have the members interconnected in that manner. So I just represent up to the point up to point A, and I forgot about the whole thing. Okay, doesn't matter. So this is the hydraulic system that we're working on. We are told to find the forces generated in cylinder EF and AD. So where is EF? EF is this point here. Okay, EF the start point. So cylinder EF, we are going to take the moments about H. This H here. Even though there is a rotation that is happening here, the sum of moments at this point is equals to 0. Okay, because it is a pin connection. So that is why I'm saying here that the sum of moments about H is equals to 0. But how do we get the moment? We will need because we are going to assume, because the question tells us that we can assume the weight of these members. Okay, so whatever that is balancing this weight here, it is this force that is injecting from here, should balance with this weight. So that is where we have in the weight, you multiply by the distance from H, the distance of this weight from H, when you add to the force here times this distance, because we need so because we've said the moment about H is equals to 0. From our free body diagram, we see that it is true, because when you take the moment about H, you realize that it is at this point whereby there's a rotation, so the sum of moments there is 0. So the force that is coming from here, it is kind of trying to balance with this weight here. So if you take a moment about H, we are taking about the force that must be produced by this arm here, so that it can lift this weight about here, or it can at least hold this weight without it trying to be, what do we say, it is said to balance this weight of this material that is being lifted. So that is why I went ahead and said the moment is given by, because we look this is okay, let us begin from here. We're saying that because it's a moment about H, we are going to get the distance between it has to be the horizontal distance between H, and where the weight is acting. Okay, so this weight, because we are given as 0.5 here, 0.5. Alright, so again we need also this distance, because it is this force. Assume this one is a force. Maybe the correct distance direction, because we are trying to counter this weight, so this one should be pulled inside. Should be pulled inside. Okay, so let us say that that is the direction of our force. Okay, so when we have a force that is facing that direction, we need now to, because it's a moment about this point, should be balancing this weight here. So we have the horizontal distance already, so we need to get now the horizontal distance, or the perpendicular distance between this point. And the perpendicular distance will be given by just the distance between this point and this point. Okay, and the perpendicular distance between H and G is basically this distance. It has to be perpendicular distance, right? Having said that, we are going to find those distances. We have the first distance. We have the first distance, which is 0.5. This is a snapshot of what we have above there. So we have 0.5, our perpendicular distance, and we have this other distance here which is not given. Okay, but what do we have from the question? We have this distance from here up to here. okay, and you have this angle. So if this one is 90 degrees, you can apply a sine rule so that we can get D, and we say sine of the angle is equals to D opposite of a hypotenuse. So if these two sides are forming an 90 degree here, it means this is the base and this is the height. So this automatically this becomes a hypotenuse. So side that is equals to opposite of a hypotenuse. That is why we are getting D is equal to 0.75 meters. Okay, and now if we have this D, now we replace here our force. We know our force because why are we saying negative? We're saying negative because when you look at this point and taking moments that are pulling this point downward, it's negative clockwise moments. This point negative, this force is negative. As we have a negative here, and the other force is this force here. It is trying to counter this weight here to lift it up, so it has to come this way. So that is why it is turning our point in that manner, clockwise, anti-clockwise. So that is why it is positive. So we have negative W here and positive EF. Okay. From there we are going to, because we are equating to 0, the only unknown is EF. We solve for EF and we get the value as 9.8 kilonewtons. So the force generated in the hydraulic cylinder EF is 9, and we have already solved for that. So this is 9,000 newtons, 9,800 newtons. That is it's a lot of force. Okay. So it is 9 and the weight of the material is 14. Yeah. Alright. Now we want to get force AD. Okay. So force AD, we find a body that does not include AD. Where is AD? Is A, is D, is E, is H, is G, and this is what was this one? That was F. That was F. Alright, very good. Where is AD? AD is from here up to here. So the force that must be generated. So because the question tells us to assume the weight of the body members. So the forces that are experienced within these parts are not going to be considered. We are only going to consider the external forces that are acting on this arm here. And that external force is W, and the other force is that is produced by the hydraulic cylinder that is acting here. Now we have distance CH. Distance CH is this, but it's not an horizontal distance. So the horizontal distance between this point and this point, because this angle is 10 degrees, this angle here from the diagram is 10. Okay, so because this one is x on the xy plane, if you want to get the horizontal component of this line here, you're going to multiply by the cos of this magnitude. Okay, we'll get that. So that is why we are saying here the horizontal distance equals to cos of this this angle. So you get this distance. So because eventually we'll be looking for a moment, and we'll need this force between point C and the weight of the material, because we'll be looking for moment about point C. Okay, yeah, because this force will tend to lift this upward, and now this one is pulling the point downward. So we have projected the distance horizontally. We multiply by cos 10. That is what I have said right now. And the other thing is the horizontal distance A is obtained by the horizontal distance that we've gotten here. We had 0.5 because from here up to where the weight is acting here, we have 0.5 from the diagram that we are is given in the question. So A is given by cosine of the sum of this plus this. Okay, so that is distance A, 2.4696. Now how are we going to apply wait, we are told W is pointing in a clockwise direction, and therefore force AD must point in the opposite direction to counter W and balance. So that is why I was saying force AD, because this one is trying to pull this point C down, this force must now be projected in that direction so that it can either balance or to counter the weight of the material. Now, coming now to point C, what do we have? So this is point C, this is D, this is A. Okay, and we have this angle here. So because this force is acting in that manner, definitely it will have its vertical component and the horizontal component. The y component, which is AD sin 60, and the x component, which is AD cos 60. And to get the horizontal distance between, because we are told this is 0.25, we need now the horizontal distance. And the horizontal distance is given by between point C and D. We are going to take 0.25 cos 10. We are just projecting that to the x-axis, and the vertical distance is going to be 0.25 sin 10. So this distance here between C and D, C and D. Having said that, this is just for illustration. I was saying that this force AD cos 60, it is trying to turn that point. This point about point C, it is trying to push it in the negative direction, and the weight that is acting at this point is trying to pull it in this manner. So we are having so negative and positive and negative. So this is negative. Why is this negative? This is point C. It's trying to okay, I see it. Okay. Yeah, because this is negative because it is acting in the clockwise direction. So see about point this force that is acting in that manner, it is actually trying to go in that direction. And this direction is the one negative. That is why we have a negative here. So that was just for illustration. moving on to finding now the moment. How do we get the moment about point C? The moment about point C is going to be given by, about point C. So we have this distance A, that is where the weight is acting from point C, and we also, what do we have? Let us first go through the equation. Okay, 80 sin 60, which is the vertical component of this force emanating from this cylinder here. 80 sin 60 is trying to push this point C up like that, and if it is pushing point C up like that, it is pushing it up. So it is positive. So if it is positive, so it is that force, the magnitude of the force, 80 sin 60, but what distance is it acting at from point C? Horizontal distance is this distance multiplied by the cos, so will give us the horizontal distance, this distance, right? Plus AD equals 60. AD equals 60 is this force here. This force now, it is acting at a distance, vertical distance, this distance which we have here. So it is AD equals 60 times 2.25 sin 10. Why is it negative? Because it is pushing it like that, because it's on top, just on top, above it. So it is trying to pull it or to push it and to move it in the clockwise direction, which is negative. And now finally we have W, which is acting about point C in this direction, alright, negative direction. So that is why we have negative. Now what unknowns do we have here? AD is the only unknown here, because you have W and all the values can be obtained. Okay, so and the sum is equal to 0. So if you simplify all this, if you take sin 60 multiplied by this, you're going to get that value, minus AD equals 60. So the whole of this value is given by that, and W is known, so W multiplied by the distance there, you are going to get 0. So AD is equals to that, 189 kilonewton. Okay, hence the force required in AD, cylinder AD, is 189.82. Yeah, that's it for that question. Thank you for watching.